Americium. Americium is a synthetic chemical element with symbol M and atomic number 95. It is radioactive and a transuranic member of the actinide series, in the periodic table located under the lanthanide element europium, and thus by analogy was named after the Americas. Americium was first produced in 1944 by the group of Glenn T. Seaborg from Berkeley, California, at the Metallurgical Laboratory of the University of Chicago, a part of the Manhattan Project. Although it is the third element in the transuranic series, it was discovered fourth, after the heavier curium. The discovery was kept secret and only released to the public in November 1945. Most americium is produced by uranium or plutonium being bombarded with neutrons in nuclear reactors. 1 ton of spent nuclear fuel contains about 100 grams of americium. It is widely used in commercial ionization chamber smoke detectors, as well as in neutron sources and industrial gauges. Several unusual applications, such as nuclear batteries or fuel for spaceships with nuclear propulsion, have been proposed for the isotope 242 MAM, but they are as yet hindered by the scarcity and high price of this nuclear isomer. Americium is a relatively soft radioactive metal with silvery appearance. Its common isotopes are 241 AM and 243 AM. In chemical compounds, americium usually assumes the oxidation state +3, especially in solutions. Several other oxidation states are known, which range from +2 to +7 and can be identified by their characteristic optical absorption spectra. The crystal lattice of solid americium and its compounds contain small intrinsic radiogenic defects, due to metamictization induced by self-irradiation with alpha particles, which accumulates with time. This can cause a drift of some material properties over time, more noticeable in older samples. Although americium was likely produced in previous nuclear experiments, it was first intentionally synthesized, isolated and identified in late autumn 1944, at the University of California, Berkeley, by Glenn T. Seaborg, Leon O. Morgan, Ralph A. James, and Albert Ghiorso. They used a 60-inch cyclotron at the University of California, Berkeley. The element was chemically identified at the Metallurgical Laboratory of the University of Chicago. Following the lighter neptunium, plutonium, and heavier curium, americium was the fourth transuranium element to be discovered. At the time, the periodic table had been restructured by Seaborg to its present layout, containing the actinide row below the lanthanide one. This led to americium being located right below its twin lanthanide element europium. It was thus by analogy named after the Americas. The name americium and the symbol M are suggested for the element on the basis of its position as the sixth member of the actinide rare earth series, analogous to europium, EU, of the lanthanide series. The new element was isolated from its oxides in a complex, multi-step process. First, plutonium-239 nitrate solution was coated on a platinum foil of about 0.5 cm2 area. The solution was evaporated and the residue was converted into plutonium dioxide by annealing. After cyclotron irradiation, the coating was dissolved with nitric acid, and then precipitated as the hydroxide using concentrated aqueous ammonia solution. The residue was dissolved in perchloric acid. Further separation was carried out by ion exchange, yielding a certain isotope of curium. The separation of curium and americium was so painstaking that those elements were initially called by the Berkeley group as pandemonium and delirium. Initial experiments yielded 4 americium isotopes, 241 AM, 242 AM, 239 AM, and 238 AM. Americium 241 was directly obtained from plutonium upon absorption of 2 neutrons. It decays by emission of a alpha particle to 237 Np. The half-life of this decay was first determined as 7002510000000000000 black spade 510 plus or minus 20 years, but then corrected to 432.2 years. The second isotope 242 AM was produced upon neutron bombardment of the already created 241 AM. Upon rapid beta decay, 242 AM converts into the isotope of curium 242 cm. The half-life of this decay was initially determined at 17 hours, which was close to the presently accepted value of 16.02 H. The discovery of americium and curium in 1944 was closely related to the Manhattan Project. The results were confidential and declassified only in 1945. Seaborg leaked the synthesis of the elements 95 and 96 on the U.S. radio show for children Quiz Kids 5 days before the official presentation at an American Chemical Society meeting on November 11, 1945, when one of the listeners asked whether any new transuranium element beside plutonium and neptunium had been discovered during the war. After the discovery of americium isotopes 241 am and 242 am, their production and compounds were patented, listing only Seaborg as the inventor. The initial americium samples weighed a few micrograms. They were barely visible and were identified by their radioactivity. The first substantial amounts of metallic americium weighing 4,200 micrograms were not prepared until 1951 by reduction of americium fluoride with barium metal in high vacuum at 1100 degrees C. The longest-lived and most common isotopes of americium, 241 am and 243 am, have half-lives of 432.2 and 7,370 years, respectively. Therefore, any primordial americium should have decayed by now. Existing americium is concentrated in the areas used for the atmospheric nuclear weapons tests conducted between 1945 and 1980, as well as at the sites of nuclear incidents, such as the Chernobyl disaster. For example, the analysis of the debris at the testing site of the first U.S. hydrogen bomb, Ivy Mike, revealed high concentrations of various actinides including americium, but due to military secrecy, this result was not published until later, in 1956. Trinitite, the glassy residue left on the desert floor near Alamogordo, New Mexico, after the plutonium-based Trinity nuclear bomb test on July 16, 1945, contains traces of americium-241. Elevated levels of americium were also detected at the crash site of a U.S. Boeing B-52 bomber aircraft, which carried 4 hydrogen bombs, in 1968 in Greenland. In other regions, the average radioactivity of surface soil due to residual americium is only about 0.01 picocuries/g. Atmospheric americium compounds are poorly soluble in common solvents and mostly adhere to soil particles. Soil analysis revealed about 1,900 times higher concentration of americium inside sandy soil particles than in the water present in the soil pores. An even higher ratio was measured in loam soils. Americium is produced mostly artificially in small quantities, for research purposes. A ton of spent nuclear fuel contains about 100 grams of various americium isotopes, mostly 241 am and 243 am. Their prolonged radioactivity is undesirable for the disposal, and therefore americium, together with other long-lived actinides, must be neutralized. The associated procedure may involve several steps, where americium is first separated and then converted by neutron bombardment in special reactors to short-lived nuclides. This procedure is well known as nuclear transmutation, but it is still being developed for americium. The transuranic elements from americium to fermium occurred naturally in the natural nuclear fission reactor at Oklo, but no longer do so. Americium has been produced in small quantities in nuclear reactors for decades, and kilograms of its 241 am and 243 am isotopes have been accumulated by now. Nevertheless, since it was first offered for sale in 1962, its price, about $1,500 per gram of 241 am, remains almost unchanged owing to the very complex separation procedure. The heavier isotope 243 am is produced in much smaller amounts, it is thus more difficult to separate, resulting in a higher cost of the order 100,000,160,000 USD/g. Americium is not synthesized directly from uranium, the most common reactor material, but from the plutonium isotope 239Pu. The latter needs to be produced first, according to the following nuclear process. The capture of 2 neutrons by 239Pu reaction, followed by a beta decay, results in 241 am. The plutonium present in spent nuclear fuel contains about 12% of 241Pu. Because it spontaneously converts to 241 Am, 241Pu can be extracted and may be used to generate further 241 Am. However, this process is rather slow. Half of the original amount of 241Pu decays to 241 Am after about 15 years, and the 241 Am amount reaches a maximum after 70 years. The obtained 241 Am can be used for generating heavier americium isotopes by further neutron capture inside a nuclear reactor. In a light water reactor, 79% of 241 Am converts to 242 Am and 10% to its nuclear isomer 242 Am. Americium 242 has a half-life of only 16 hours, which makes its further up conversion to 243 Am extremely inefficient. The latter isotope is produced instead in a process where 239Pu captures 4 neutrons under high neutron flux. Most synthesis routines yield a mixture of different actinide isotopes in oxide forms, from which isotopes of americium can be separated. In a typical procedure, the spent reactor fuel is dissolved in nitric acid, and the bulk of uranium and plutonium is removed using a Purex-type extraction with tributyl phosphate in a hydrocarbon. The lanthanides and remaining actinides are then separated from the aqueous residue by a diamide-based extraction, to give, after stripping, a mixture of trivalent actinides and lanthanides. Americium compounds are then selectively extracted using multi-step chromatographic and centrifugation techniques with an appropriate reagent. A large amount of work has been done on the solvent extraction of americium. For example, a 2003 EU-funded project codenamed Europart studied triazines and other compounds as potential extraction agents. A bistriazinyl bipyridine complex was proposed in 2009 as such a reagent is highly selective to americium. Separation of americium from the highly similar curium can be achieved by treating a slurry of their hydroxides in aqueous sodium bicarbonate with ozone, at elevated temperatures. Both Am and Cm are mostly present in solutions in the +3 valence state, whereas curium remains unchanged. Americium oxidizes to soluble M complexes which can be washed away. Metallic americium is obtained by reduction from its compounds. Americium fluoride was first used for this purpose. The reaction was conducted using elemental barium as reducing agent in a water and oxygen-free environment inside an apparatus made of tantalum and tungsten. An alternative is the reduction of americium dioxide by metallic lanthanum or thorium. In the periodic table, americium is located to the right of plutonium, to the left of curium, and below the lanthanide europium, with which it shares many similarities in physical and chemical properties. Americium is a highly radioactive element. When freshly prepared, it has a silvery white metallic luster, but then slowly tarnishes in air. With a density of 12 G/cm3, americium is less dense than both curium and plutonium, but has a higher density than europium mostly because of its higher atomic mass. Americium is relatively soft and easily deformable and has a significantly lower bulk modulus than the actinides before it, Th, Pa, U, Np, and Pu. Its melting point of 1173 degrees C is significantly higher than that of plutonium and europium, but lower than for curium. At ambient conditions, americium is present in its most stable alpha form, which has a hexagonal crystal symmetry, and a space group P63/mmC with cell parameters A equals 346.8 pm and C equals 1124 pm, and 4 atoms per unit cell. The crystal consists of a double hexagonal close packing with the layer sequence A back, and so is isotypic with alpha lanthanum and several actinides such as alpha curium. The crystal structure of americium changes with pressure and temperature. When compressed at room temperature to 5 GPa, alpha Am transforms to the beta modification, which has a face-centered cubic symmetry, space group FM3M and lattice constant A equals 489 pm. This FCC structure is equivalent to the closest packing with the sequence ABC. Upon further compression to 23 GPa, americium transforms to an orthorhombic gamma Am structure similar to that of alpha uranium. There are no further transitions observed up to 52 GPa, except for an appearance of a monoclinic phase at pressures between 10 and 15 GPa. There is no consistency on the status of this phase in the literature, which also sometimes lists the alpha, beta, and gamma phases as I, 2 and 3. The beta-gamma transition is accompanied by a 6% decrease in the crystal volume, although theory also predicts a significant volume change for the alpha-beta transition, it is not observed experimentally. The pressure of the alpha-beta transition decreases with increasing temperature, and when alpha americium is heated at ambient pressure, at 770 degrees C it changes into an FCC phase which is different from beta-am, and at 1075 degrees C it converts to a body-centered cubic structure. The pressure-temperature phase diagram of americium is thus rather similar to those of lanthanum, praseodymium, and neodymium. As with many other actinides, self-damage of the crystal structure due to alpha particle irradiation is intrinsic to americium. It is especially noticeable at low temperatures, where the mobility of the produced structure defects is relatively low, by broadening of X-ray diffraction peaks. This effect makes somewhat uncertain the temperature of americium and some of its properties, such as electrical resistivity. So for americium 241, the resistivity at 4.2 K increases with time from about 2 ohm cm to 10 ohm cm after 40 hours, and saturates at about 16 ohm cm after 140 hours. This effect is less pronounced at room temperature, due to annihilation of radiation defects. Also heating to room temperature the sample which was kept for hours at low temperatures restores its resistivity. In fresh samples, the resistivity gradually increases with temperature from about 2 ohm cm at liquid helium to 69 ohm cm at room temperature. This behavior is similar to that of neptunium, uranium, thorium, and protactinium, but is different from plutonium and curium which show a rapid rise up to 60 K followed by saturation. The room temperature value for americium is lower than that of neptunium, plutonium, and curium, but higher than for uranium, thorium, and protactinium. Americium is paramagnetic in a wide temperature range, from that of liquid helium, to room temperature and above. This behavior is markedly different from that of its neighbor curium which exhibits antiferromagnetic transition at 52 K. The thermal expansion coefficient of americium is slightly anisotropic and amounts to 69947499999999999 blackspade times 10⁶ degrees C along the shorter axis and 6994620000000000000 blackspade times 10⁶ degrees C for the longer C hexagonal axis. The enthalpy of dissolution of americium metal in hydrochloric acid at standard conditions is 2994379400000000000 blackspade 620.6 plus or minus 1.3 kJ/mol, from which the standard enthalpy change of formation of aqueous M3+ ion is 2994378800000000000 blackspade 621.2 plus or minus 2.0 kJ/mol. The standard potential M3+/M0 is 2999792000000000000 blackspade 2.08 plus or minus 0.01 V. Americium readily reacts with oxygen and dissolves well in acids. The most common oxidation state for americium is +3, in which americium compounds are rather stable against oxidation and reduction. In this sense, americium is chemically similar to most lanthanides. The trivalent americium forms insoluble fluoride, oxalate, iodate, hydroxide, phosphate, and other salts. Other oxidation states have been observed between +2 and +7, which is the widest range among the actinide elements. Their color in aqueous solutions varies as follows: M3+, M4+, MvO+2, MvIO2+2 and MvIIO5-6. All oxidation states have their characteristic optical absorption spectra, with a few sharp peaks in the visible and mid-infrared regions, and the position and intensity of these peaks can be converted into the concentrations of the corresponding oxidation states. For example, Am has two sharp peaks at 504 and 811 nm, M at 514 and 715 nm, and M at 666 and 992 nm. Americium compounds with oxidation state +4 and higher are strong oxidizing agents, comparable in strength to the permanganate ion in acidic solutions. Whereas the Am4+ ions are unstable in solutions and readily convert to M3+, the +4 oxidation state occurs well in solids, such as americium dioxide and americium fluoride. All pentavalent and hexavalent americium compounds are complex salts such as KAMO2F2, Li3AMO4, and Li6AMO6, Ba3AMO6, AMO2F2. These high oxidation states Am, and M can be prepared from M by oxidation with ammonium persulfate in dilute nitric acid, with silver oxide in perchloric acid, or with ozone or sodium persulfate in sodium carbonate solutions. The pentavalent oxidation state of americium was first observed in 1951. It is present in aqueous solution in the form of Amo+2 ions or Amo3 ions, which are however unstable and subject to several rapid disproportionation reactions. 3 americium oxides are known, with the oxidation states +2, +3, and +4. Americium oxide was prepared in minute amounts and has not been characterized in details. Americium oxide is a red-brown solid with a melting point of 2205 degrees C. Americium oxide is the main form of solid americium, which is used in nearly all its applications. As most other actinide dioxides, it is a black solid with a cubic crystal structure. The oxalate of americium, vacuum dried at room temperature, has the chemical formula M237H2O. Upon heating in vacuum, it loses water at 240 degrees C and starts decomposing into AMO2 at 300 degrees C. The decomposition completes at about 470 degrees C. The initial oxalate dissolves in nitric acid with the maximum solubility of 0.25 G/L. Halides of americium are known for the oxidation states +2, +3, and +4, where the +3 is most stable, especially in solutions. Reduction of M compounds with sodium amalgam yields M salts, the black halides AmCl2, AmBr2 and AmI2. They are very sensitive to oxygen and oxidize in water, releasing hydrogen and converting back to the M state. Specific lattice constants are: americium fluoride is poorly soluble and precipitates upon reaction of M3+ and fluoride ions in weak acidic solutions. The tetravalent americium fluoride is obtained by reacting solid americium fluoride with molecular fluorine. Another known form of solid tetravalent americium chloride is KAMF5. Tetravalent americium has also been observed in the aqueous phase. For this purpose, black Am4 was dissolved in 15 MnH4F with the americium concentration of 0.01 m. The resulting reddish solution had a characteristic optical absorption spectrum which is similar to that of AmF4 but differed from other oxidation states of americium. Heating the M solution to 90 degrees C did not result in its disproportionation or reduction, however a slow reduction was observed to M and assigned to self-irradiation of americium by alpha particles. Most americium halides form hexagonal crystals with slight variation of the color and exact structure between the halogens. So, chloride is reddish and has a structure isotypic to uranium chloride and the melting point of 715 degrees C. The fluoride is isotypic to LaF3 and the iodide to BiI3. The bromide is an exception with the orthorhombic PuBr3 type structure and space group CM-CM. Crystals of americium hexahydrate can be prepared by dissolving americium dioxide in hydrochloric acid and evaporating the liquid. Those crystals are hygroscopic and have yellow-reddish color and a monoclinic crystal structure. Oxyhalides of americium in the form AmViO2x2, AmVO2x, MiVOx2 and MiIIOx can be obtained by reacting the corresponding americium halide with oxygen or Sb2O3, and ammocal can also be produced by vapor phase hydrolysis. The known chalcogenides of americium include the sulfide AmS2, selenides AmSe2 and Am3Se4, and tellurides Am2Te3 and Amte2. The pnictides of americium of the AmX type are known for the elements phosphorus, arsenic, antimony, and bismuth. They crystallize in the rock salt lattice. Americium monosilicide and disilicide were obtained by reduction of americium fluoride with elementary silicon in vacuum at 1050 degrees C and 1150-1200 degrees C. MSI is a black solid isomorphic with La-Si, it has an orthorhombic crystal symmetry. M6 has a bright silvery luster and a tetragonal crystal lattice, it is isomorphic with PuSi2 and ThSi2. Borides of americium include AmB4 and AmB6. The tetraboride can be obtained by heating an oxide or halide of americium with magnesium diboride in vacuum or inert atmosphere. Analogous to uranocene, americium forms the organometallic compound americene with 2 cyclooctate tetraene ligands, with the chemical formula 2Am. A cyclopentadienyl complex is also known that is likely to be stoichiometrically AmCp3. Formation of the complexes of the type Am3, where BTP stands for 2,6-dipyridine, in solutions containing NC3H7 BTP and M3+ ions has been confirmed by exafs. Some of these BTP-type complexes selectively interact with americium and therefore are useful in its selective separation from lanthanides and another actinides. Americium is an artificial element of recent origin, and thus does not have a biological requirement. It is harmful to life. It has been proposed to use bacteria for removal of americium and other heavy metals from rivers and streams. Thus, Enterobacteriaceae of the genus Citrobacter precipitate americium ions from aqueous solutions, binding them into a metal phosphate complex at their cell walls. Several studies have been reported on the bioabsorption and bioaccumulation of americium by bacteria and fungi. The isotope 242MAm has the largest cross-sections for absorption of thermal neutrons, that results in a small critical mass for a sustained nuclear chain reaction. The critical mass for a bare 242MAm sphere is about 914 kg. It can be lowered to 35 kg with a metal reflector and should become even smaller with a water reflector. Such small critical mass is favorable for portable nuclear weapons, but those based on 242MAm are not known yet, probably because of its scarcity and high price. The critical masses of 2 other readily available isotopes, 241Am and 243Am, are relatively high, 57.6 to 75.6 kg for 241Am and 209 kg for 243Am. Scarcity and high price yet hinder application of americium as a nuclear fuel in nuclear reactors. There are proposals of very compact 10 kW high-flux reactors using as little as 20 grams of 242MAm. Such low-power reactors would be relatively safe to use as neutron sources for radiation therapy in hospitals. About 19 isotopes and 8 nuclear isomers are known for americium. There are 2 long-lived alpha emitters, 241Am and 243Am, with half-lives of 432.2 and 7,370 years, respectively, and the nuclear isomer 242M1M has a long half-life of 141 years. The half-lives of other isotopes and isomers range from 0.64 microseconds for 245M1M to 50.8 hours for 240Am. As with most other actinides, the isotopes of americium with odd number of neutrons have relatively high rate of nuclear fission and low critical mass. Americium 241 decays to 237 Np, emitting alpha particles of 5 different energies, mostly at 5.486 MeV and 5.443 MeV. Because many of the resulting states are metastable, they also emit gamma rays with the discrete energies between 26.3 and 158.5 keV. Americium 242 is a short-lived isotope with a half-life of 16.02 H. It mostly converts by beta decay to 242 cm, but also by electron capture to 242Pu. Both 242 cm and 242Pu transform via nearly the same decay chain through 238Pu down to 234U. Nearly all of 242M1Am decays by internal conversion to 242Am and the remaining 0.459% by alpha decay to 238Np. The latter subsequently decays to 238Pu and then to 234U. Americium 243 transforms by alpha emission into 239Np, which converts by beta decay to 239Pu, and the 239Pu changes into 235U by emitting an alpha particle. Americium is used in the most common type of household smoke detector, which uses 241Am in the form of americium dioxide as its source of ionizing radiation. This isotope is preferred over 226Ra because it emits 5 times more alpha particles and relatively little harmful gamma radiation. Element collector Theodore Gray mentions in his book The Elements, a visual exploration of every known atom in the universe. You might think that a synthetic radioactive element that follows plutonium and has a significantly shorter half-life would be some kind of superbomb material, available only to scientists in secret laboratories. Perhaps a mad scientist is studying americium in a lair somewhere, but if you want some yourself you can simply walk into any neighborhood hardware store, supermarket, or Walmart and buy some, no questions asked. The reason is not that americium is fundamentally less dangerous than the elements around it. In fact, the commonly available isotope, 241Am, is significantly more radioactive than weapons-grade plutonium, and at least as toxic. No, the difference is simply that there is a useful application for americium that requires only a very tiny amount, and for which a company was prepared to go through the effort required to carve out and get a regulatory exception. The amount of americium in a typical new smoke detector is 1 microcurie or 0.29 microgram. This amount declines slowly as the americium decays into neptunium-237, a different transuranic element with a much longer half-life. With its half-life of 432.2 years, the americium in a smoke detector includes about 3% neptunium after 19 years, and about 5% after 32 years. The radiation passes through an ionization chamber, an air-filled space between two electrodes, and permits a small, constant current between the electrodes. Any smoke that enters the chamber absorbs the alpha particles, which reduces the ionization and affects this current, triggering the alarm. Compared to the alternative optical smoke detector, the ionization smoke detector is cheaper and can detect particles which are too small to produce significant light scattering. However, it is more prone to false alarms. As 241Am has a roughly similar half-life to 238Pu, it has been proposed as an active element of radioisotope thermoelectric generators, for example in spacecraft. Although americium produces less heat and electricity, the power yield is 114.7 MW/G for 241Am and 6.31 MW/G for 243Am, and its radiation poses more threat to humans owing to neutron emission. The European Space Agency is considering using americium for its space probes. Another proposed space-related application of americium is a fuel for spaceships with nuclear propulsion. It relies on the very high rate of nuclear fission of 242Am, which can be maintained even in a micrometer-thick foil. Small thickness avoids the problem of self-absorption of emitted radiation. This problem is pertinent to uranium or plutonium rods, in which only surface layers provide alpha particles. The fission products of 242Am can either directly propel the spaceship or they can heat a thrusting gas. They can also transfer their energy to a fluid and generate electricity through a magneto-hydrodynamic generator. One more proposal which utilizes the high nuclear fission rate of 242Am is a nuclear battery. Its design relies not on the energy of the emitted by americium alpha particles, but on their charge, that is, the americium acts as the self-sustaining cathode. A single 3.2 kg 242Am charge of such battery could provide about 140 kW of power over a period of 80 days. Even with all the potential benefits, the current applications of 242Am are as yet hindered by the scarcity and high price of this particular nuclear isomer. The oxide of 241Am pressed with beryllium is an efficient neutron source. Here americium acts as the alpha source, and beryllium produces neutrons owing to its large cross-section for the nuclear reaction. The most widespread use of 241Am-Be neutron sources is a neutron probe, a device used to measure the quantity of water present in soil, as well as moisture/density for quality control in highway construction. 241Am neutron sources are also used in well logging applications, as well as in neutron radiography, tomography, and other radiochemical investigations. Americium is a starting material for the production of other transuranic elements and transactinides. For example, 82.7% of 242Am decays to 242 cm and 17.3% to 242 Pu. In the nuclear reactor, 242Am is also upconverted by neutron capture to 243Am and 244Am, which transforms by beta decay to 244 cm. Irradiation of 241Am by 12C or 22Ne ions yields the isotopes 247Es or 260Db, respectively. Furthermore, the element berkelium had been first intentionally produced and identified by bombarding 241Am with alpha particles, in 1949, by the same Berkeley group, using the same 60-inch cyclotron. Similarly, nobelium was produced at the Joint Institute for Nuclear Research, Dubna, Russia, in 1965 in several reactions, one of which included irradiation of 243Am with 15N ions. Besides, one of the synthesis reactions for lawrencium, discovered by scientists at Berkeley and Dubna, included bombardment of 243Am with 180. Americium-241 has been used as a portable source of both gamma rays and alpha particles for a number of medical and industrial uses. The 59.5409 keV gamma ray emissions from 241Am in such sources can be used for indirect analysis of materials in radiography and X-ray fluorescence spectroscopy, as well as for quality control in fixed nuclear density gauges and nuclear densometers. For example, the element has been employed to gauge glass thickness to help create flat glass. Americium-241 is also suitable for calibration of gamma-ray spectrometers in the low-energy range, since its spectrum consists of nearly a single peak and negligible Compton continuum. Americium-241 gamma rays were Al.